And we're talking about gases, right? So let me come back over here and make sure my marker's in the right color. Yep, red. And I'm going to do a couple problems here, but I want to point out that mostly what we're doing, ready for this, is short cuts. And I like shortcuts, right? I know you do too. I will say, sometimes I don't use them because they're hard to remember. So shortcuts are sort of like, you gotta remember what to do. So anyway, the shortcuts are molar volume of a gas, really molar volume of a gas at STP, right? You would have known that, okay? So that's just a new thing. Molar volume of a gas at STP, the density of a gas, and the molar mass of a gas, okay? So let me point out what we're going to be doing here for all three of these is we're going to be saying the molar volume, that is the moles per what? Liter, right? That's the molar volume. And what is the density? That's going to be grams per liter, right? Or grams per mil, right? Or kilograms per liter. Agreed? That's what density is. So I think we're typically going to find this in grams per liter just because the numbers are going to be so small. Gases are not very dense, right? But either way, all right, so that's what we're looking at for density. And what's the molar mass of a gas? You tell me, the units. All right, I know that's my question's maybe too open-ended. I should have apologized at the outset of this movie. At this video, I've got, I'm working in the middle of a bunch of my colleagues here. They're all working too. And I'm afraid there's going to be a little bit of background noise. So we'll do our best, and I hope it's not distracting. So the molar mass of a gas, what are the units of that molar mass? It's going to be grams per mole, right? And so if in a previous section we figured out, I got a little girl running back and forth, and she thinks I can't hear her because she's running on her tippy toes. Molar mass of a gas, so we're going to need moles, liters, grams, and liters, or grams and moles, right? And so we can figure all those things out. We're good, right? Well, the way we're going to get that is we're going to say, watch this, PV is equal to nRT. All right? So, and then of course we're going to go from moles, that is N, to mass in grams via formula weight, right? So we can really get all these things. These are all just shortcuts. All right, that said, let me erase all that and talk about these one at a time. We're still on molar volume, okay? So molar volume, and as I said, let me go back to red here. Red is in STP. Now you might say, what is STP? STP is standard temperature and pressure. So what I'm going to do is I'm going to go to the book. I'm in section 5, chapter 5, section 5. And STP is described on page 189 as T is equal to 0 degrees centigrade, and P is equal to 1 atmosphere. Okay? That's standard temperature and pressure, STP. That has to be memorized, by the way. There's no way you would know that. I mean, it sort of makes, it's going to fit nicely in your head. 0 degrees Celsius and 1 atmosphere. All right, so if we know that, the molar volume, watch this, of a gas, P, V, N, R, T, and we know if the molar volume is going to be the mole per liter, right? That's the units of it, because that's what molar volume is, mole per liter, right? Now watch this. At STP, it's going to be 1.00, 1 liter, 1 liter, N, oh, that's what we're looking for, R, 0.08206 liter atmospheres per mole Kelvin, and temperature is 0 degrees Celsius, which is 273 kelvins. Watch this now. This is amazing. So PV is equal to nRT. PV is equal to nRT. N is equal to PV over RT. P is 1. Volume is 1. 0.08206. 273. You're not going to believe this. Okay, pause the video. You should calculate this. You're being too passive. I can see you sitting there at your computer sucking on a chili dog. And sucking on a chili dog and not paying attention. You should calculate that. 1 divided by 0.08206. 1 divided by 0.08206 divided by 273 equals okay. So this comes out to be 0.00 nope 0.04464. Okay, so watch this now. This is going to be, that's moles, right? I'm running out of space here. Can I come over here? Let me come over here and say 0.004464 moles per liter is the molar volume. Now watch this. We could also say that how many liters per mole. And this is the, well, you have to memorize this, okay? This is going to imply, you have to memorize this number, but watch. The other number is easier to memorize, and that is 22.4. Okay, so this is something that you can memorize. The molar volume of an ideal gas is 22.4 liters per mole. And I just showed you how I calculated it, okay? I know I'm dragging this video out. 22.4 liters per mole of an ideal gas. All gases are 22.4 liters per mole. So Tro on page 189 has a picture, thank you William, has a picture of these gases. So suppose that you've got helium at STP. Temperature 273 Kelvin, pressure 1 atmosphere, because it's at STP, right? R is equal to 0.08206, and we could let's put N to be 1 this time, and we'll calculate for V, and we'll find that it goes wham, 22.4. Isn't that cool? Okay, and we do the same thing over here, right? STP for, I mean, they're all 22.4. I guess the point is it doesn't matter what the gas is, whether it's xenon, helium, or methane. At STP, it's 22.4. So you can memorize that. Thank you so much. I'm good. Yeah, of course you can. 22.4 liters. Here's the big point. 22.4 liters of an ideal gas per mole of that gas. Okay? All right. So let me go back then to the other point, density. And this, I'm not even going to use a shortcut for this. You guys can use shortcuts. I will tell you what the shortcut is. On page 190, Tro derives a formula. He takes the density and he defines it as the, watch this, the molar mass over the molar volume, right? And you see that turns out to be mass per volume. I'm not going to calculate this all out, but I'm going to show you that it comes out to be the density, several steps, which are all on page 190. Thank you, William. Several steps come out to be this. Density, which I typically draw as a capital D, he draws as a lowercase d. Watch this. Is equal to the pressure times a script m over RT, where the script m is the density in grams, I'm sorry, Just 1 second here. Let me verify this. I'm going to make sure I'm not getting sideways here with you. Where the script m is the molar mass, right? And this is going to give us, watch this, in atmospheres, molar mass is grams per mole. Liter atmospheres per mole Kelvin and Kelvin. So this is going to give us, see, the atmospheres will cross off, the moles will cross off because they're in the denominators, kelvins will cross off. It's going to give us the density in grams per liter. Can you see that? Okay, so this is the molar mass. And you're welcome to memorize this formula here. I don't even think I'm going to demonstrate it. I do not like this. This is a shortcut I don't like. Okay? And then finally, the molar mass of the gas is calculated, as you can see, well, the same way. Okay? The molar mass of the gas is here. If the density is equal to the then the molar mass, that's a script m, I know it's ugly, but that's what Tro uses, is equal to dRT over P, okay? And so here's another equation which you can use. This is not a mu, that's a script m, sorry. And here, so there's two equations here. I'm going to call this equation 2 and this equation 3. And the first thing that you memorized here is there's 22.4 liters per mole of an ideal gas. Okay, so these are the three shortcuts I promised you at the beginning of this video. So let's do 2 examples and then we'll be done. So the first example is calculate the density of nitrogen gas as 125 degrees Celsius and the pressure of such and such, okay? So what I'm going to do is I'm going to go PV is equal to RT. I'm ultimately going, I warned you, right? I'm not going to use the shortcut here. I don't like it. Sometimes I do and sometimes I don't. So calculate the density. So if the density, I'm so used to using a capital D. Okay, may I do that? You're going to be doing this. Those of you who want to use the shortcut are going to be doing that. Okay? It's shorter, but you have to remember the equation, so I don't like it. So density is going to be in grams per liter, right? So all I have to do is find grams in liters, and I'm done. So P, V, N, R, T. Pressure is 755. How do you spell 755? 2 5s, I think. 755 millimeters of mercury. Will give me atmospheres. Calculate the density. All right, I'm going to go ahead and choose that volume to be 1 liter. Aha. That's one trick I've got to use. Okay, I'm just choosing it to be 1 liter. The moles is what I'm going to calculate. 0.08206 liter atmospheres per mole Kelvin, and the temperature is 125 degrees Celsius plus 273 is going to give me kelvins. And I can't do that. Well, yeah, I can. I can do that. I'm going to come over here and do it. 125 plus 273 is 893. 398 Kelvin. You know what? Next time I'm going to give you the blessing of listening to one of my children calculate that, because they need to practice. If they're ever going to be like their dad, they've got a lot of work to do. That's a joke, by the way. It's not really too funny, I guess. But 755 divided by the mom's sitting right here. She doesn't think that's funny. All right, 755 divided by 760. Is equal to 0.9934, 0.9934 atmospheres. 1 liter, 0.08. Oh, we're done, aren't we? Look at that. 0.9934 atmosphere. Sorry about the background noise. I warned you that I have got things going on, right? I do hope it's not too distracting. 0.08206. This was in liters. This is in liters. Atmospheres per mole Kelvin. I'm patiently putting all those things in there, right, to help you practice crossing things off. Atmospheres cross off, liters cross off, kelvins cross off, and I'm left with moles in the denominator of the denominator. So actually, you know what I'm going to do? I'm going to put the moles up here and get rid of it down here, right? So that brings the moles all the way up top, which I knew. I was calculating moles in the first place, right? So let's calculate this number. You calculate it too. You should pause the video. I insist. 0.9934 times 1 divided by 0.08206 divided by 390. I ruined it. Just a moment, please. 0.9934 divided by 0.08206 divided by 398 equals 304.165. 304.165. That just doesn't sound right. That can't be right. No. Nope. That makes no sense, right? Because look, this number is almost 1. And there's 1. How can you get 300 if you divide by these two numbers? Look, I'm going to do this again. 0.9934. Oops, that's why, because I didn't put the point in there. It was 9,000. 9934 divided by 0.08206 divided by 398 equals 0.0304. Okay, that makes sense. 0.0304165. Yeah, that makes sense. Right? You see why that bothered me? It was about 1 times 1 divided by 0.08 divided by 398. There's no way it could be 300. Okay, so that's how many moles I have. Well, I knew I started out with 1 liter, so I got to convert this now to grams, and then I'm almost done. Right? How do I do that? Well, this we've done over and over and over. I promised you would come back and back and back. So I'm looking for grams, and I have moles, right? Looks like I'm going to multiply by the formula weight. Agreed? Boom, 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 and boom. So that looks like this is my formula weight, or my molar mass. So, which Tro is using a script M there, right? I'm going to take that and multiply by my formula weight. So what's the formula weight of nitrogen gas? Aha. Don't forget, it's a diatomic molecule. The formula weight of nitrogen gas is 28 point. Looking at my periodic table, nitrogen's 14.01, so N2 gas, nitrogen gas is going to be 28 point, oops. Ah, man, sorry. 28.02 grams per mole. So I'm going to take that number and multiply by 28.02 times 28.02, and I'm going to get 0.85227. 0.85227, right? Grams. I was looking for grams per liter, but I chose 1 liter, so it's the same. Therefore, the density, 8.5, and now we've got 3 sig figs, 852 grams per liter. Wow, I love it. Oh. Okay. What do you think? Beautiful, huh? Okay, so let's do another problem. And this time, let's do the molar mass. No, I warned you I'm not going to use, let me go back to red. I'm not going to use the shortcut. Okay, you've got a nice shortcut there in front of you, but I'm not going to do that. I'm just going to go fall back and use my PV is equal to nRT. A sample of a gas has a mass of this. Uh-oh. Uh-oh. Mass. (0.311 grams, 55 degrees Celsius. Plus 273 is going to give me 55 plus 273, 328. Kelvins. Got some latency, 0.08206. Liter atmospheres per mole Kelvin. And its pressure, it's okay, I got my volume here too, 0.225 liters. And its pressure is 886. What is that? 886 millimeters of mercury. (886) divided by 760 equals 1.1658. 1.1658 atmospheres. Can you see how I'm just going to calculate moles and then I'm going to get my grams per mole? Like that's ultimately what I'm going for, right? Is grams per mole. Okay? So I'm just going to calculate moles here. And PV is equal to nRT. I love it. N is equal to PV over RT, which is equal to 1.1658 atmospheres. Hopefully you're starting to look at these questions and say, wow, they all look the same. 0.225 liters. 0.08206. Liter atmospheres per mole Kelvin, and 328. Okay, kelvins. Kelvins cross off, atmospheres cross off, liters cross off, and I've got a denominator in my denominator, so I'm going to go ahead and take it up to the numerator. And I knew I was going to have that because it was moles anyway, right? So 1.1658 times 0.225 divided by 0.08206 divided by 328 equals 0.009. Hopefully, I don't know, that doesn't sound right, does it? 0.0097453 moles. You know, let's think about this. This is about 1, and that's about 1/5, okay? So yeah, I expect a small number here. So it's about 1/5 or 1/4 divided by 0.08 divided by 3. Yeah, it's good. We'll come back. We'll see if this molar mass makes some sense. So this looks like it's going to be, the grams is 0.311 grams divided by 0.0097453 moles is going to give us grams per mole, right? So let's do that. Let's take 0.311 and divide it by that mass. What is it, 0.311? Yeah. So this gives us 31.913. 913 grams per mole. That is the molar mass, or script M as he's using, okay? And there's our answer, 31.913. Okay? I think I give too many sig figs here. There's 3 sig figs, 3 sig figs, 3 sig figs, and 3 sig figs. This looks like 2, right? But it goes to 3. So if this goes to 3 sig figs, I should report this as 31.9 grams per mole. All right? What do you think? Tell me you love it. Tell me you love it. All right, good work.